very much, Hussein and ITAMP, and all of you. You don't know me yet because I just arrived in the middle of the snowstorm in a little tiny car. I'd like to welcome you all, though, to the Thursday evening of the Zoosh. Skiing after down to the. I'm one of the, like many of the lecturers, not exclusively the only one. I'm one of the old timers in strong field ionization, and although I've been working along with Linda Young and many other people in the strong field X-ray part of this for a while, I thought that in my first lecture would be a really good idea to pull back and go to when Tony Starris and Paul and all of us were kids, and we were first getting this. So I will say a little bit about that in this first lecture. Strong field photoionization, that is before high harmonics. What can we learn from all the electrons that don't end up making high harmonics or attosecond pulses? So that's the first lecture. I'll return to X-rays in lecture 2. Lecture 2 for me is going to be on X-ray free electron laser basics. That is what's inside the box. Those of us who are experimentalists always like to know what's inside our laser box. And lecture 3 will be on the thing that's closest to my current research, which is transient impulsive X-ray methods, which we think is a path to realize molecular movies in a somewhat different approach than the other areas of attosecond. Okay, so you won't get to meet up with any of these guys, but they all helped me not only with this presentation but all of my research. So here's my group, probably the strongest group that I've ever had. I have right now. And then also, I assume all this stuff gets posted, and I have a few really general references that do dig down into the background a little bit more. And also want to acknowledge Lou DeMauro, Marcus Gurr, and Adi Natan especially for helping with some of these slides. So let's get to it. So this is by now such a familiar and iconic picture for all of you. You know what this is. You draw a little funnel and you say, that's not a funnel, that's a Coulomb potential. I know that. And you draw a little wiggle and say, that's not a wiggle, that's a bound electron. Right? I know that too. And this is tunnel ionization. Now, what you probably also have heard, but maybe it wasn't emphasized too much, is that there's a static model prediction here for when the ionization should happen independent of quantum mechanics. And that is that this electron, just by the fact that one of the walls of its confining potential goes away in a strong field, it will ionize, and the critical field for that in atomic units, which of course we are all using atomic units in this lecture. Atomic units, yes. And atomic units is just the square of the ionization potential divided by 4. That's the static model prediction. Now, in the early days, this prediction was tested. It's easy to test. You just try it out with a lot of atoms that have different ionization potentials. And it looked like this. It was just a shockingly accurate estimate, particularly if you put it on log-log scales where there's 4 decades on each axis, that you hide lots of sins. But look at all of these. These are basically all the rare gases plus their readily accessible ionization stages. And they all hang out in their ground states until you get to some critical field, which is given by this formula, and they ionize. This was first noticed way back in 1989 by Steve Ochs at the University of Rochester and a bunch of other people. I think Meyerhofer definitely down the street like this around. Okay, so that's static, but the field we're applying isn't static. So what happens after? Now we get to the stuff that I'm sure Paul and everybody else covered, the ponderomotive energy of a free electron, which is addressing the continuum. So here's, again, it's not a wiggly line, it's an oscillating electric field. We all know that by now. And classical physics tells us that the energy of the electron in this wiggling is the ponderomotive potential energy that scales like the square of the electric field in scales like the inverse square of the driving frequency, meaning it's a very, very big deal for microwaves, a super big deal. And that's what all this physics comes from. It comes actually from this word Ponder motive. It comes from people who studied inverse Bremsstrahlung and low-density plasmas driven by microwaves. That's where it comes from. And actually, I think, Paul, maybe you even come from that background too. Okay, so I don't. I'm a laser jock through it, but I know about this because in those early days, we realized that was a big scaling. 1 electron volt worth of kinetic energy at 800 nanometer laser light for about 2 times 10 to the 13 watts per square centimeter, very easy to get to. Now, the thing I want to point out with respect to photoionization spectroscopy, which maybe hasn't been talked about too much yet, is that this Ponder motive energy is not quantized. It can be greater than or less than the quantum of the electromagnetic field, and it's big compared to that. It's big compared to that, or at least on the same scale. So it should dominate. Quantization shouldn't dominate. It should dominate. You would think. One would think. Let's see how that affects the ionization process. Okay. Well, first we might want to make sure that we're not completely leaving quantum mechanics behind. So there's quantum treatment. Perhaps this has also been alluded to, but this is much more important for the photoionization of the electrons. Well, I'll go over it a little bit. This is particular treatment that I'm talking about is due to Amos. I may have not even spelled those names right. I was writing this in such a hurry, but I think Amos, Delany, and Kranoff are spelled correctly. They said that let's not think of this as a classical process. Let's think of this as a quantum tunneling process. We have an approximately wedge-shaped barrier that our electron has to tunnel through. Real easy to calculate it if we even approximate it as a wedge. And we get some formula. That's a static field formula for the tunnel current. And from that you get a tunnel decay rate, a decay constant. However, we know that this is in the process of changing all the time. It's oscillating back and forth, but it's oscillating very slow. So at any given instant, it's kind of static, but we have to integrate over that time. That's the idea. That's the whole calculation that they did. The rest is just, left as a homework problem if you really want to redo it. And you get that the result, the rate for ionization, then should scale like all the things you know it should scale. First, the shape of the potential. So there's a z dependence. Also, it's how big the field is. So there's a field dependence. That's what this square root of I is. There's a question about how deeply bound the electron is. That's what n star is. It's the effective, assuming a hydrogenic model, it's the effective quantum number of the binding energy of the electron. Sometimes called the effective quantum number. And then there's a couple of other sets of constants. D is just dependent on those same quantities. Okay, so you get that, and what you find if you try to ionize using this formula is that it works pretty well. Well, so did the static field formula. So they're not that terribly at odds with each other. And a characteristic ratio of timescales comes out, which is exactly the one you'd imagine needs to be dealt with. And that is, what wins, the tunnel rate or the oscillation of the field? So in one cycle, do you get everything out, or you only get a little out, you got to wait for the field to turn around again. That ratio is characterized by this parameter gamma, the Keldysh parameter, which can be put in terms of the ionization energy and the Ponder motive potential. And if the Keldysh parameter is 1, that means you have equality for those rates. So if it's smaller than 1, then you're in the tunnel regime, where tunneling is fast, and if it's larger than 1, tunneling is slow, compared to that characteristic cycle. Okay, that's enough hand waving. Let's let the computer wave its hand a little bit and take a look at what the classical prediction is for the drift of an electron if it's created at a particular time during a laser pulse. So here is a laser pulse. This is the trajectory of the electron, classical trajectory. The rule is that it's created at 0 velocity, and this is this is time, this is distance from the atom. So you can see it sailing away from the atom up, or on the other half cycle it will come down. And you also see that on the way out it gets a few wiggles. Okay. The drift energy clearly depends on when the ionization happens during the pulse. Let's see if I can move on here. Okay. So following the ionization, acceleration in the field leads to that drift energy. So here again is that oscillating field, sine omega t electric field. Okay? And the ionization happens at some instant during that cycle. And I can characterize the time simply by a phase. It's the phase during one cycle. Presumably this could happen on any cycle, and will happen again on the next cycle. But let's just consider this phase as the sort of surrogate for the time in units of radians of the electric field cycle. At that time, this tunneling or over the barrel, whatever happens, and you create an electron with 0 velocity, and then it sails, and you saw its trajectory in that classical simulation. Now, if this time is 4 degrees past the peak, then here's what the trajectory looks like. And you end up, after the pulse has gone by, with an electron that's sailing off in this negative direction with a certain velocity. What happens if I move this a very tiny amount? Let's go from 4 degrees past peak to 8 degrees. It has a huge effect on the drift energy. So the drift energy is extremely sensitive to the time of ionization. So remember that when we start talking about the spectrum. We're going to see some fast electrons, and we're going to see some slow electrons. And we now have a model, albeit a crummy classical model, but look how well it works in things like the total ionization rate. Not bad, right? Right, Ken? Not bad. Not bad. So, it says 4 degrees past, 8 degrees past, that determines, that tiny amount determines that energy. So we'll think about that. All right. By the way, it's just a classical formula, that dependence of the final velocity on the phase. And so I just wrote it out. This is assuming that you start out with 0 velocity when you ionize. You could question that assumption too. Okay. So, now, electrons are quantum mechanical objects, right? Some thinks they are. And that means that I have to worry about which path type stuff and add up paths, right, that result in the same final state. So in this case, the final state is an electron with a certain velocity. So here are some electrons that I tried to catch when they exited with the same velocity, but they were clearly produced at different times. In fact, electrons with the same energy are made many times over a laser pulse. We were just discussing this, in fact. How many times are they made per cycle? How many times is this velocity made per one cycle? Hands? Come on.
Twice.
Twice. Twice. Roughly speaking, once when the electron just goes out in always feeling the force in the direction that pulls it in its ultimate direction of its ultimate velocity, and once when it actually started the other way and turned around. Twice per cycle, cycle after cycle after cycle, it all adds up coherently. What should we expect? If the trajectories are constructive, then the electron current is enhanced. And so we expect periodic maxima in the photoelectron spectrum, and we see it. Okay? The earliest, well, I got to say that Pierre Agostini, who actually did see this first, didn't have very good data. But within a couple of years, there was great data like this that showed that, yeah, this really, yeah, here, this constructive interference of trajectories, man, electrons are really quantum mechanical. This is really great. Oh, cool. Right. You know, it's really, really tempting to forget about all this classical ionization stuff now and say, no, that's just a multi-photon process. Look, it's a multi-photon process, right? I can line up the arrowheads of multiple photons that start from the ground state, zoom right past the ionization potential after 1, 2, 3, 4, 5, 6 photons, and keep on going. And it's really tempting to show that. I succumbed to that temptation myself back in my youth. It's actually misleading. That's what people say when, what was it that Pauli said? Correct me if I'm wrong, I think it was Pauli who said, that isn't even wrong. So it has that aspect. It's misleading. Okay, here's another one. This happens to be in xenon. And it was made with a typical intense laser of the day being 30 years ago, around a 30 picosecond long pulse, 1 micron, so it was probably neodymium doped YAG laser, focused to about 30 terawatts per square centimeter, this magical 10 to the 13 coming right in. That's exactly what we would expect. See this beautiful ATI spectrum, and I think my first clip will show, yep, they match right up. They match right up. They match right up. What about all that ponderomotive energy, though? Well, one way to think about that, since the spacing is 1 photon, and the angular distributions are also consistent with perturbation theory, one way to think about that is that it really is multi-photon, except the atom is strongly affected by the field, by this sort of oscillating field. Its bound states acquire this need to wiggle. They get distorted. And that distortion raises the ionization potential so that it takes more work to go from the ground state of xenon, where the electrons are all tightly bound, to anywhere near this ionization potential where one of the electrons is like a free electron, it's very loosely bound. So what that suggests is that it just takes more work to ionize the atom. And the amount of extra work that it takes, assuming that not much is happening to the tightly bound ground state. Let's see, I'm trying to think of the Pan, Eberle, and Armstrong, right? Those were the 3 theorists who demonstrated that nothing much should be going on with this ground state back in the old days in a very simple, elegant way. So this picture they were very much in favor of. They reinforced the idea that it just takes more energy to ionize, but then it's really just multi-photon. And that predicts that these low peaks you shouldn't see because they're round. You know, they don't produce electrons, and sure enough, it is suppressed. It is suppressed. The trouble is, if those bound states are acquiring extra energy, then what about all these electrons? Aren't they acquiring extra energy too? And how come I don't see that wiggle energy has to be added in or subtracted off from the drift? Subtracted off, I guess, would be the right thing, from the drift. And so why isn't it smear everything out? Why not? Okay, well, actually people figured it out. The reason is that this ponderomotive energy, this wiggle energy, actually acts like an effective potential energy in a time-averaged Hamiltonian sense. So my electrons, once freed, once they're several angstroms away from their paired ion, they ain't coming back no more. They will get to my detector. But on the way to the detector, they have to get out of the laser focus. So this is the focus of my laser, a much more macroscopic object than just the field of the Coulomb field of an atom. These free electrons might have been produced from an atom here, or here, or here. And if they were produced here, they were produced with a lot of wiggle energy, here with just a little. But they have to get out of that ponderomotive potential. And that skiing out, if only we had If only we were at Les Ouches. There are all kinds of puns I could make here. That departure of the electrons from a more or less static, not changing very fast, ski slope converts their wiggle energy efficiently through just conservation of energy into drift energy. And so we see the electrons with all of their energy converted into drift, even though we know that we made them with a lot of wiggle and a little drift. That's the idea. So the Pondermoto ski run, how long does it take? Back of the envelope will tell you that it takes a few picoseconds for the kind of ways we can focus a laser. Now, how many of you are, or at least are in an aspirational way, if not actually professional at the moment, how many of you are theorists? I should have asked it the other way around. How many of you are experimentalists? Ah, okay, well I shouldn't be talking to you folks. Well, you know how well you can focus a laser beam? Probably. Do you know how well you can focus a laser beam? Yeah. Excuse me?
What do you mean?
Well, how small is this wave? That would be really good. It's bigger because it's practical stuff. There's a vacuum chamber about this big, and I have a few millijoules that I'm trying to focus it to only tens of terawatts per square centimeter and stuff like that. Anyway, you put all those numbers in, and it turns out that this is many tens of microns across, maybe even 100. 100 would be big, but it wouldn't be crazy. And so it takes some time. It takes several picoseconds for the electrons to get out. So it's a good thing, it's a darn good thing that we were back in the Stone Ages and only had tens or 100 picosecond lasers so we could see all that physics. Otherwise, we would have just missed it. Okay? Well, 1990 comes along and ultra-fast science starts to embrace femtosecond technology. And we know that in a femtosecond, these electrons hardly move. So all that quantum mode of energy should just vanish. You won't be able to convert it into drift energy anymore. So I'll get to that in a second. So I wanted to summarize. I wanted to go even slower. I hope you're not sleepy yet, but I'm trying to go so slow. What I do is as I get this sort of pattern going, I start telling jokes and I look at people. It's a way of going slow. You may have noticed this if you teach. You notice it. Anyway, what have we learned so far? Well, we've learned that in this oscillating field, ionization happens at a rate that depends on the distortion of the field, maximum ionization up top, and that the escape velocity depends on where it was ionized to, maximum escape velocity down low. We learned that. We also learned that this above-threshold ionization spectrum is actually a little bit complicated. First of all, it's all displaced by the Pondermoto potential. You can see that from the channel suppression. We learned that. We also learned that some kind of tunneling or ADK idea controls how these pulses are dropping off faster and faster and faster, and that you more or less don't see much going on anymore after the most energetic electrons, which happen about, if they were ionized right at the zero crossing, you'd have to worry about how that happens. Then they would come out at an energy of 3 UP. That's 2 Pondermoto potential units for the shape of this curve, and 1 because of this displacement. We learned all that. We've learned all that. Now we go to short pulses. Short pulses, which again came in the early 90s, they should suppress, late 80s, early 90s, it's all the same, should suppress Pondermoto conversion to drift energy. They should suppress it because you can't ski anymore. So we should see all that smearing out of the above-threshold ionization spectrum. So we tried it way back in the old days when we first got our handle on some short pulses. And we did see, you could say it's kind of smearing out. Actually, it doesn't really look like smearing out. It looks like a lot of really sharp structure. Okay? Really, really sharp structure. In fact, if you're an old atomic spectroscopist like I am, it not only looks like a lot of really sharp structure, man, that looks like a Rydberg series if I ever saw one. That's just got to be a Rydberg series, right? It's got to be. So, a little mysterious. What's happening there is the role of, well, the Rydberg states, the role of the high-line intermediate states is beginning to come in to assist ionization. You're getting a little enhancement of the electrons that are produced up here or up here, because along the road they were in resonance, multi-photon resonance, with some bound state. And depending on how much AC start shift there was, they could be shifted into resonance for this red state, or for this sort of light-colored state, or for this dark blue state. And every one of those will make a different peak. The size of the peak will depend on the order of the multi-photon resonance, and also the intensity, which drives how fast how intense this multi-photon process is. And so really this is a form of spectroscopy. This is it sort of removes the idea that you have spatial and temporal averaging, and gives you those shells, those small tori inside your focus where you happen to be in resonance at that time for different states. Now, let's take another look at electron trajectories. The same picture I showed before. Now, you know that when the trajectory returns to the origin here, that means it's recolliding. And of course, that's what leads to high harmonics. That's what most of the real excitement is about these days, all those high harmonics. But also it can lead to rescattering. That is a different kind of a process, either elastic rescattering, which I'll talk about mostly, but even inelastic rescattering. That is, one channel is go back to the ground state, another channel is go to some excited state, a third channel is don't get any state, just scatter and stay in the continuum. All those things can happen. You can see, for example, at certain ionization times that you get very, very low velocity returns. Other times you get higher velocity returns, and you can also get multiple returns. Those are really high velocity returns. Now, how should we understand this reapproach to the core? Well, a really cool idea, which I'm just going to touch on just so that you know it, is let's go into an accelerating reference frame. Since so much of our physics depends and scales as the wiggling motion of a free electron, let's just make that the origin of our coordinate system. We'll put the origin of our coordinate system on the locus of an oscillating electron. Well, I hate to tell you, but that is not an inertial reference frame. So what? What happens if you have non-inertial reference frame? Does physics stop? Oh, it does. You get fictitious forces. Well, I guess because we call them fictitious forces, maybe that sort of means that physics does stop. Anyway, you get fictitious forces, but you can see kinematic quantities in a new light. In a new light. That's my first pun on light. So, for example, let's take a look at these ionizations where we said that we had, by the way, there's a name for this. This is the Kramers-Henneberger frame. That's the oscillating frame. Let's take a look at this strong field ionization, where in our approximation, electrons start at zero velocity when they're ionized. Now, in the oscillating frame, zero velocity means that in a one dimension this way versus time plot, where I have oscillating coordinates, oscillating with the electric field, it means that the electrons are going to move in straight lines, but they're going to be ionized at a point where they are at the same place and time as an ion. The at-rest ion now looks like it's the one that's oscillating, but of course it's only its coordinate that's oscillating. It's not. And the point of contact here is a tangent, because they have the same velocity at the beginning, that is, they're at zero velocity. Okay? So it's every tangent. This is kind of cool. This means that I have a graphical construction now of the kinematics of strong field ionization. Well, let's take a look at it, see what we can learn. Okay. Here, for example, are three very closely spaced projectors. You know, these are the ones I showed you. 4 degrees, 8 degrees, right? We saw that a small change in phase made a big change in velocity. Well, now you see why.